Here we have a collision followed by ballistic motion. Let me draw a diagram of what's going on here. So we've got a block, we'll call that M2 on the edge of the table, and then we have a bullet here, M1, moving at some speed V1I. The table is 1.4 meters high. Let's see, we have M1 is 22 grams and M2 is 360 grams. And then we're told that after the bullet hits the block, the bullet becomes embedded in the block, and the two combined things land 2.3 meters away horizontally from the base of the table. That's where M1 plus M2 eventually lands. And we want to know V1I. We know the V2I is 0. This thing is originally at rest. Okay, well, so let's start with the collision. We have, this is just a collision in one dimension, so I don't need to split it into components. So we'll write down our basic conservation of momentum equation for two masses, and I'm going to recognize that V2I is 0, and that V1F and V2F are just VF, right? So that'll be our final velocity after the collision, will be M1 plus M2 VF. The final velocity after the collision, VF for part 1, is V0 for part 2, right? Final velocity for part 1 is equal to the initial velocity for part 2. This is done here except for, well, I've got 0.022 V1I is 0.382 times VF. So I can't solve this, so I'm going to leave it. Now let me consider the ballistic motion. Now I'm going to try to use the ballistic motion of the mass, the combined masses, to figure out the initial velocity for part 2. If I can find the initial velocity for part 2, then that's the final velocity for part 1, and I'll be done. So this is a problem from chapter 3, and if you don't know how to do this, then you should go back and review chapter 3. You certainly should have this done before you watch this part of the video. You really ought to know how to do this. But in case you don't, or if you want me to do it for you, here's how we do it. Anytime you've got ballistic motion, we're going to split this up into x and y components and write down what's given for each component. Now I'm going to establish a sign convention that to the right is positive and down is positive, since generally that's the direction of motion. If that's the case, then delta x is 2.3, delta y is 1.4. The initial x velocity is, I don't know. The initial y velocity is 0 because it's initially moving horizontally. Final x velocity, I don't know. Final y velocity, I don't know. Now it's in free fall, right? When it's in free fall, then the acceleration is 9.8 meters per second squared directed downward. So it has 0x component, and the y component is positive 9.8 meters per second, right? Because we've decided that down is positive. Time is unknown. Alright, so my goal is to get this V0x, but I can't do it yet. I do have 1, 2, 3 of my 5 things known in y. So let me solve for t, and then I'll use that time over here in x. So the equation that doesn't have final velocity in it is here, and so that gives me 1.4 is equal to 0 plus 4.9 t squared. So the time it takes for the mass to fall, 1.4 meters, is 0.535 seconds. So I'll use that in the x direction. And so in the x direction, I have delta x is v0 xt plus 1/2 at squared, and that term is 0. So 2.3 is equal to v0 x times 0.535 So V naught x is 4.3 meters per second. That's equal to my initial velocity for the ballistic motion, which is my final velocity for part 1. Okay? That plugs in right here as the final velocity for part 1. So now I'm going to take this equation and bring it down here. I got 0.022 V1I is equal to 0.382 times 4.3. And so V1I is 75 meters per second.